let you know. So I'm starting to record. So these presentations are not graded. They are not part of the competition in that they are not something that is going to be used for comparing you to other groups. They're to kind of make sure everybody has sort of a good starting point, a good beginning for some of the content and understanding. Welcome, Dr. Oma. As I mentioned to the students, some of you might be joining us. So,
hello.
And I already mentioned to them that you are not judging them, that this is not about grading them, that this is about evaluating the program. So, the presentation that you give, again, the idea is to hear what you have learned and to give you feedback. And it doesn't matter if you've learned everything perfectly. I am still going to have some questions for you and some extra feedback for you to try to ensure that everybody's kind of starting from the same place. That's all. I'm really delighted to meet all of you. I'm a little bit new to this program, as I mentioned. This is my first year helping with ExMASS. Andy's been leading it for many, many years. So do any of you have questions for me before we begin? All righty. Well, please proceed then. And I'm not going to stop you or interrupt you until after you're done, and then we'll chat about it.
Okay, so I am trying to share a presentation, and I'm not sure if I am or not. I kind of lost it.
Right now we see your screen, but we don't see the presentation. We can, yeah.
Oh, good.
Great.
Good? Okay.
Perfect.
All right, so we're good to go. Fee, you're on. All right, maybe Ellie, can you pick up for Fee?
Okay. Hi, we are Upper Darby High School's Lunar Planetary Club, and this is our Asteroid and Moon 101 presentation.
This image here depicts impact craters with a range of sizes that formed by meteors colliding with the moon's surface. We can tell that this large crater is quite old because smaller craters have occurred on top of it after its original formation. The larger craters formed first and then the smaller ones.
The lava channel is a sinuous rill, meaning it is a large fissure formed from a depression on the moon that likely were formed from collapsed lava tubes, as you can see by the separation of the channel and the lack of craters on top of the channel compared to the rest of the surface allows us to understand that it's younger. The right largest crater is an endogenic crater, which could have been formed from a combination of impact as well as general weathering and erosion over time on the moon.
So in this image, we're looking at three primary features. So we're looking at this lunar rill, which was formed early in the moon's history as a result of lava flow. And it intersects with an impact crater formed by a meteor collision with the moon's surface. And this crater likely formed after the lunar rill because the lunar rill doesn't interrupt its structure. The crater seems to be imposed on top of the rill. And then we have these mountain-like structures over on the right, which, although mountains on the Earth are formed by tectonic activity, this likely wasn't formed by tectonic activity because the moon doesn't have tectonic plates. So rather, it was more likely due to moon rock being driven up at the site of the impact of a large crater.
This image is an image of the asteroid Itokawa, and it is most commonly thought by scientists that asteroids are early formations of solar systems. And although they are known as the larger versions of meteoroids, most asteroids lack the mass to form a definitive shape. And you can see that on as the oblong asteroid right there in the center.
So we can see on the surface of asteroid Itokawa, it's covered with a lot of rubble rather than large rocks. And the largest dimension of the body is only 0.5 kilometer. So this lines up with the common theory that asteroid Itokawa was derived from a larger celestial body. And also, there are no definite impact points upon the asteroid. So it's a little bit harder to compare to other bodies in space.
This is an image of asteroid Vesta, which has a mean diameter of 525 kilometers, which means it's massive enough that gravity has been able to pull it into a spherical shape. The leftmost crater is superimposed on the right one, meaning that it's newer. And the troughs are older than all of the smaller craters because they have formed on top of it. And the troughs could have been formed either by a collision with another asteroid, causing the ground between faults to shift apart and the ground to fall in, or a asteroid hitting the South Pole, causing the asteroid to spin and the equator to bulge out, forming the troughs.
This last slide depicts the asteroid Eros. This picture has the smallest scale of any in the slide. It is only about 12 meters across, which explains the lack of any apparent impact craters. The two features that are present, though, are boulders and regolith. The boulders are remnants of meteorites that collided, broke apart, and then landed on Eros. The regolith is sand-sized particles that coat the surface. They were also formed in collisions with other bodies, wherein those celestial bodies were pulverized.
We at the Upper Darby High School would like to thank you for tuning into our presentation.
Thank you. Nice job. Very succinct. First of all, I wanted to talk to you about the presentation style, and then I'd like us to go through the slides one at a time and chat a little bit about them, okay? First of all, I like the use of color. It's vibrant. I like you were nice and loud and clear and had great roles. The slides themselves, in many cases, they had a fair amount of text where I was struggling to read the text and listen to you at the same time. So I recommend, when possible, bulleting it so that it's not full sentences, but just, a few words, and then say what you want to say. That tends to work better for most presenters. There are people, including senior scientists, who write lots and lots of words, but people will be able to understand what you're saying and pay more attention to you if there's fewer words. Ms. Roseanne, could we go ahead and start from from not the very first introductory slide, but the second slide? And we'll talk a little bit about some of what you all had to say and ask you some questions. Thank you. All right. So on this slide, first of all, you all use the word meteor. Can you tell me a little bit about meteor versus meteoroid, meteorite, asteroid? Sort of what the differences in those terms are? People use them interchangeably all the time. Go ahead, Max.
Yeah, so asteroid is like usually they're bigger than meteors and meteorites, and they occur in space in general. And I think meteorites are rocks that have come down and landed on a surface and then been like, yeah. So we observe them on after they've already collided with the surface. And then meteors are, I believe that they're more, like we observe them in orbit around the sun. And yeah, I'm not exactly sure on the exact differences. But.
Okay. There's many people conflate the terms, and so you'll see them used incorrectly all the time. And so that makes it really confusing for everybody else who's trying to learn, right? A meteor is the streak of light that you see in the sky, sometimes called a shooting star, as a meteoroid burns up in our atmosphere. So a meteor is just the light that you see as something is burning up in our atmosphere. Something that's hitting the ground, you're absolutely right, is a meteorite, whether it lands on the Earth, or there might be meteorites from the Earth that landed on the Moon. We have meteorites from Mars that have landed on the Earth, meteorites from asteroids. Meteoroid is a small rock in space. Many meteoroids are about the size of a grain of sand, actually. So many of them are really tiny. And you're right, there's sort of one place where it becomes an asteroid instead of a meteoroid if it's a certain size. Absolutely. And asteroids can orbit the sun. Many of them do. Meteoroids can orbit the sun. They can also orbit asteroids, you know. Anyway, as soon as you start to orbit planets, they become moons. But anyway, you get the idea. So in the presentation, I wanted to make sure that you understood that meteor is just a streak of light. So in this slide, when you use the term meteor, you probably mean asteroid, or sometimes you'll see scientists just use the word impactor so as not to have to define for sure whether it was a comet or an asteroid. But we think that in many of these cases they probably were asteroids as opposed to comets, but yeah. When you're looking at the one that you've circled, you're absolutely right, it is quite old. Yes, there's a lot of craters on top of it, so clearly it's had time to get extra craters. Is there anything else that you can tell about the one that you've circled compared to some of the smaller ones that might tell you that it's older? Anything else about it that besides the number of craters? The number of craters is absolutely true.
The size of it?
There can still be big impacts more recently, although tell me more why you say that, because I think I know what you're getting at there a little bit as well. Is it Nishat? Tell me more about what you're thinking of.
It's Nishat, and I just figured that the longer it is, I guess it just, I don't know. I don't know. I forgot the reason.
Early on in the solar system, a lot of the really massive things were still around, running into things. And I don't know if you all had the chance to spend a little bit of time looking into the late heavy bombardment, also sometimes called the lunar cataclysm. So we think that about 3.8 billion years ago, there's evidence right now from the chemistry of many of the rocks that we brought back from the moon that there were a lot of huge asteroid impacts back then. Things that might even be so big that you might be hesitant to call them asteroids. Huge impactors back then. And nowadays we don't have a whole lot of giant, enormous asteroids running into things. But back then we did, early on in the solar system formation. Some of the really enormous ones were more likely to have happened back then than they are more recently. But there's been constant impacts ever since. It's just that there were a lot of them, 3.8 billion years ago. So some of the research talks a little bit about that. Yeah, some of the most biggest basins that have the Mare in them were probably from then. Also around the asteroid, the crater that you've circled there, do any of you see some of those features there? Some of those lines? in the box that you've got on the side there, you might be able to see what looks like little scratches. This is the site of the Apollo 12 landing site, and those little scratches around the crater are tracks from the astronauts walking around, and they had a little trolley that they were using to help them carry things. And so those little lines around the crater are from where the Apollo 12 astronauts were walking around. One of the other features in terms of that tells us that this one is older is that it kind of looks more smoothed out. You can see some of them look more smoothed out where they're not as sharp, not as distinct. So as asteroids get older and they keep getting covered with debris from other impacts forming over time, they might kind of start to look a little smoother, a little less sharp. So older craters look less sharp. Older craters definitely have more impacts in them. And then the last thing is that the older ones tend to be darker and the younger ones tend to be brighter. Over time, interaction with stuff from the sun, particles and radiation from the sun, darkens the lunar surface. So the craters here that you see that are much brighter, some of the smaller ones, if you're looking, do you see some that are kind of really bright compared to others? Those tend to be younger as well. One last question for you about this picture. How could you tell that these are craters and not hills? Does anyone want to go? Max? Mm-hmm.
Yeah, well, my thinking was that there was, like, there's a number of, they're all of different sizes, these craters, right? And if they were hills, you wouldn't think that they would have this type of spread, and they all have a consistent lighting. So that indicates, since it's all sizes, you'd say that these are all just meteor impacts of different sizes, and yeah.
Yeah.
So.
You're right. The lighting has a lot to do with it. Sometimes the lighting, it can trick us, right? Things can look like they're hills when they're actually craters. So if some of them, if you see how the light for all of them is kind of more on the right side and not so much on the left side, if some of them had the lighting switched around, those might be hills. But yeah, it can trick our eyes a little bit. Awesome. Okay, let's go on to the next one. Oh, I'm sorry, one more question. Those craters, how would you describe them? When you describe them as, did you all study what different types of shapes of craters there are? Would you call these simple craters or complex craters?
These would be simple craters because there's no elevated point within the center and they're small in size. Exactly
right. All of these are simple craters. Thank you, Daniel. All right, sorry. Let's go on to the next slide. You're exactly right. This is a sinuous rill depression. It could have been carved by the lava on the surface, or it could have been an underground collapsed lava tube. Either is possible. When the astronauts went here, they weren't able to go inside to get materials from the inside, which might have given them some more information. This is one of the areas, this is part of Hadley Rill. This is a close-up of one of the next slide. So it's an area where the Apollo 15 astronauts went. And you're right that we've got a crater over there on the right-hand side there, that dark area. At first, I wasn't 100% sure that that was a crater and not a volcanic mound or a volcanic dome. I had to look it up myself because it's kind of hard to tell. But yeah, it is a crater, an impact crater. Do you see right above where it says 1.2 kilometers, do you see how the terrain there is kind of bright? Any ideas why it might be brighter there than the rest of it?
I sort of just assumed that the way that the sun was hitting the moon at the time the picture was taken, I was assuming this is the reason why some things or brighter than others, and it would also explain why the crater was difficult to understand if it was a crater or if it was more of a mound, because the way the sun hits it and the way our eyes perceive it is often wrong. So I was assuming that it was just the sun at a certain level.
That's I would have assumed that at first as well, personally. We'll talk about it when we get to the next slide. I don't have any other questions for you about this slide. Do any of you have any questions for me about it? The next slide actually will give us a bigger view of it. So the previous one was a close-up of one of the areas. You see where your orange arrow is pointing to? That's sort of a close-up of a close-up of that spot right there. So you're absolutely right. This is a lunar rill, a sinuous rill. And you're right that the moon doesn't have plate tectonics. It does have, as you say, it does, now that I can read it, it does have some tectonic activity where, well, it has moonquakes, of course, and it has places where, do any of you want to tell me a tiny bit, you don't have to go into great detail, about what types of tectonic activity the moon might have, or why it might have some tectonic activity? Or what features might form from it? You're right that it doesn't have plates. I'd like you to imagine a balloon that you inflate, and then you stick it in the freezer and it starts to get cold. What does it look like when it starts to cool off? Have any of you seen an experiment where they did that?
Yeah, when liquids, like when water cools, it expands. So when things freeze, you see expansion.
When water is very unique in that water expands.
Usually it's the opposite with most other surfaces and materials.
Right. So if the air inside of the balloon doesn't expand, if it shrinks, what's going to happen to the balloon?
Well, if the material inside the balloon begins to contract, then it's not going to be able to uphold that almost spherical structure, and it'll cave in a bit.
Will it develop divots, or what do you think it'll look like? I heard somebody whisper it.
It would develop like crinkles, right?
Crinkles. Exactly. Wrinkles. Our moon has wrinkles. Our moon, as it cooled off, shrank. And it's got wrinkle ridges, also called thrust faults. So it's got these faults, cracks where it wrinkled. So yeah, that's some of the tectonic activity that I'm referring to here. It's not tectonic faults, but not what you've probably studied, right, where you've studied, faults going, where you've got plates moving this way or plates moving this way or plates moving this way. Instead, it's sort of a little bit like but they're not really subducting. They're just kind of crumpling. So, yeah, exactly. Let me come over here to the chat. Thank you, Uma. Okay, so yeah, we've got, and you're right. Most of the mountains on the moon are from impacts, and from that early on in the moon's history, those enormous asteroids that made the giant. When you look at the moon and you see the man in the moon, or the woman in the moon, or the rabbit in the moon, those giant holes in the moon, those were from early on, and those also created faults in the ground, which are the places where lava later came up through and filled in and made basalt on the surface, which is what. So looking at this picture right here, can you tell me anything about what some of these different things might be made out of? The area where the rill is, first of all, how would you describe that area where the rill is? Would you describe it as highlands? What would you describe that as?
So I think that the kind of like more to the top left of this picture is like the lunar mare area.
Yeah.
And then more towards the bottom right is where the highlands are.
You're exactly. And do you know what the difference in terms of what they're made out of is?
I don't know the exact difference, but I believe that the mare was it's a remnant from like volcanic activity, whereas like the highlands have developed kind of after, I guess. I'm not sure if that makes sense.
Actually, the highlands did not develop after. The highlands, the area that you're seeing that the highlands, and if you look at the highlands, if you look at the moon, if you go out and look at the moon, you see two different colors, right? You see dark and you see brighter areas. The brighter areas on the moon are the highlands, and they're made out of predominantly a type of rock called anorthosite, and we think that that formed first as part of the original crust of the moon. And then the mare basalt, the mare are filled in with basalts, and that's the dark rock. And basalts are the type of rock that makes up the ocean floors here on the Earth. And it's the type of rock that comes out of certain volcanoes, like the ones in Hawaii, are mostly basalt. It's got a lot of iron compared to, say, Mount St. Helens. So the dark areas on the moon are mostly flat because they got flooded with volcanic basalt a long time ago, after the highlands. So the highlands are first, the whole crust of the moon, and then later you've got those giant impactors making these giant holes in the moon and including some cracks in the moon's crust, and then after that you have the basalt flooding out onto the surface of the moon. And so the dark areas that you see to the upper left are the basalts, the mare basalts, and the bottom right, you're right, are the highlands made out of anorthosite. The rill that we see, so I just told you the highlands came first and then came the mare. What about the rill? Did it come before or after the mare?
Wouldn't the rill have come after the mare?
Yeah,
because the mare would have to cool over time to allow it to get into the shape that it is.
exactly. You can't form a river in dirt if the dirt's not there. So yeah, absolutely. What about the crater that you have circled? What's the order of that? Was that first or last, or?
Yeah, I think we talked about it in this slide here that the creator would have had to come after.
You're right, absolutely.
It like goes over top of it.
It goes over the top of it. So yes, that's the order. So you've got the highlands first, and then the mare. One of the ways you can tell that the mare came after the highlands is because, do you see how it kind of fills in the borders around the highlands? So it filled in the edges. That's a process called embayment. It's filling in the bays. So awesome. All righty. And I have Roseanne, if you remind me, I'm going to send you a couple of links to things that might be a little bit more helpful on some of this. A lot of the writing that Andy sent everyone was particularly technical, and I kind of went cross-eyed reading it myself. I've got a couple of other sources that are for adults, but are not technical at all, that might be useful for some of this as well. So I'd like to send that to you afterwards if you remind me, okay? Let's go on to the next slide. Itokawa, awesome. And yes, it's small. And you're the second group that's told me that you think that this is probably part of a larger asteroid. I don't know. I don't know if that's true or not. Maybe. You're exactly right that a lot of these small asteroids didn't have enough mass to form into a circle, so they're strangely shaped. And this is likely more of a rubble pile, a bunch of different rocks being held loosely by their gravity, absolutely. And you're right that it doesn't have any visible craters. Any idea why it might not have any visible craters? Does that mean that it's young? Why wouldn't it have craters? It's not that it's too small.
Yeah, one reason I was thinking it was like so loose that if it had like a large impact on it, the asteroid couldn't really handle it, like being as it's loosely held together right now.
So it would probably come apart and maybe come back together again. In fact, that's one of the things that might have happened to it, that it kind of came apart and slowly over time came back together again for a large impact. But what about us? Well, it's pretty small, so it'd have to be a really small impact. But we have impacts on the moon that are tiny little things. Any other ideas?
It could be that like when it has a really small impact, it kind of like absorbs it and it becomes like a part of rubble that's already there. It kind of settles among all like the dust that's already there.
Settling, yeah. You've got you've got all this dust and all these rocks, and they are kind of, every time something hits it, it kind of shakes it up and it moves around a little bit more. It's like I heard Andy describe it as like a box of cereal that you're constantly shaking. The reason for the rocks that are on the surface isn't necessarily just because those are things that have run into it. There's some people who have suggested this process. Have you noticed if you have like a box of cereal that has different shapes in it? Sometimes when you take it out, all certain things are on the top and other things are all at the bottom. Or a package of nuts. What's the nut shape that's always at the top? The big one that a lot of people don't like, and they're always at the top. It's named after a country in South America.
The Brazil nut.
The Brazil nut. So some people have called this the Brazil nut effect because the Brazil nuts are always sitting there on top, and you have to dig past them to get to the almonds and the pecans and stuff. So some people have suggested, and this is a model, so I don't know how heavily tested it's been, but they call it the Brazil nut effect, where you've shaken up the rocks that make up this asteroid often enough that the bigger rocks have moved to the top of the asteroid surface, and all the dust keeps slipping underneath them as it gets shaken over and over again by little things running into it. Make sense? So that could be one of the reasons why it's got all those rocks on top. And every time it shakes, the craters have disappeared and you can't see them. Other people have suggested that Itokawa is actually predominantly two bodies. You can see over on the right-hand side, there's sort of that bend, like maybe there's one piece here and one piece here, but still a rocky rubble pile of two bodies that have kind of joined. So we're still figuring it all out. Good points here. Let's go on to the next one. I love Vesta. It's one of my favorite asteroids. You are exactly right. It's massive enough that it's been pulled into a spherical shape. You're right about which crater is superimposed. The one that's on top of the other one is newer. And the troughs there, a rift. Those troughs go all the way around the asteroid, all the way around. And if you see other pictures of Vesta, you can see where it's got this enormous impact on one side of it. An impact that might have been close enough that, if it was any bigger, probably would have shattered this thing. We have a lot of meteorites on the Earth that have the same chemical composition as Vesta. And so we know that lots of pieces of it came off, and a number of them have eventually, over time, made their way to the Earth. Maybe they broke off in big pieces, and those big pieces were smaller asteroids, and then things ran into them and made them into little pieces. I don't know. But something that caused sort of this trough that we see around it, which is amazing. Vesta is something called differentiated, as opposed to the last asteroid we just saw. I wanted to find out, one of the groups that I've talked to hadn't really heard of that term before. Have you guys and gals, have you folks heard the term differentiation before when it comes to like asteroids and planets? Nope. Okay. It helps us understand why we get the different types of meteorites we have, in fact, when you were kind of covering different types of meteorites. So you know how the Earth has a core and a mantle and a crust? And the crust is made out of rocks that are predominantly silicates, so they're lighter. They floated up to the top. Back when the Earth was first forming and it was hot and all molten, the lighter stuff floats to the top, and then the things that are iron, they sink down to the middle. When you have a moon or an asteroid that gets hot enough that it partially melts, and this only happens for things that are fairly big, the mass creates gravity, which creates, all that force, and that force plus the impactors hitting it on the outside and things like that adds up to enough energy that they can melt completely. And this allows that differentiation. And then they start to cool off and they start to solidify in different areas. But our moon differentiated. It's got a core and a mantle and a crust. And in the process of being molten at one point, we think that the ocean, that the surface of the moon was probably covered by an ocean of magma, and that caused the anorthosite rocks, the crystals, to float up to the top because they are less dense. Vesta, we believe, is differentiated. It has the right density and the right compositions, as far as we can tell, to have become round, and then for it to have a core and a mantle and a crust. Whereas the last asteroid you saw, this rocky rubble pile, it's too small. And it seems to mostly be made out of a bunch of rocks that were never differentiated. So let me give you one more analogy for differentiation. If you have a gallon of Rocky Road ice cream that's got, nuts in it and marshmallows and chocolate, if you just take a scoop, it's going to have a little bit of everything, right? So some of the rocks from that last picture that we saw, Itokawa, would have a little bit of everything in them. But if you let that Rocky Road ice cream melt, your nuts are going to fall down to the bottom and all of the marshmallowy stuff is going to go to the top. Then if you take a scoop out of it, that scoop is either mostly going to be marshmallows, or if you take a scoop out of the bottom somehow, if you get all the way down to the bottom and scoop the bottom, it's mostly going to be the nuts. Some of the meteorites that we have are little bits of everything. The Rocky Road ice cream, undifferentiated. Some of the meteorites that we have on Earth from asteroids are just iron. That tells us that they came from an asteroid that was blasted into pieces and had chunks of its core that had differentiated. Some meteorites that we have are just the fluff on top of it, just mostly, they still have iron, but it doesn't have solid iron and it's more like the crust. So we have meteorites from the crust of asteroids, and we have meteorites from the core of asteroids, and we have meteorites that are this weird combination that look like they're at the boundary between the core and the mantle of an asteroid. So anyway, I just wanted to let you know that in case you guys decide to research meteors, asteroids, meteorites, learning a little bit more about that. Any questions before we go on to the last slide? Let's go on to the last slide here. Okay, Eros. So, can you think of another reason now for why there aren't any impact craters based on what we just talked about for Itokawa? Why might we not see any impact craters here?
Well, similar to what Nick said, regolith would have covered them up, kind of.
Would have filled them in, exactly. You're right, it's Eros, and the crumbles there are indeed regolith. I've heard Andy correct people and tell them that the boulders are also could also be considered regolith. Regolith is fine-grained, but it's also bigger rocks too, chunks of rock, pieces of rock. So the boulders could also be considered regolith as well. Everything here some of it could be pieces from when things first formed in our solar system. Some of that rocky road ice cream I was talking about, pieces that formed at the beginning of the solar system. But some of them could be results from collisions because these things have been running into each other for billions of years now. So, great. I love it. That's everything I have to share. Do any of you have any other questions for me? I really appreciate all of your time and all of the energy that you put into this. It's a lovely presentation. And you've learned a lot in a really short time. So I think you all are doing great. Ms. Roseanne, do you have any other comments or questions?
Good, thank you so much. Thanks for all of your feedback, we appreciate it.
I really appreciate it. Also, for your formal presentation during the competition phase later, make sure that you end it with, that you have, it doesn't have to be your last slide, but that you have a slide citing your resources, citing what you used as well, your references. Dr. Uma, do you have anything that you wanted to say while you're here with us?
I just wanted to, I was actually typing in the chat to everybody. This was an awesome experience. Thank you so much for allowing me to listen to you. I learned a lot from all of the students as well as from you, Christine. So this was wonderful. Thank you.